Most of your life you've been studying with real numbers. Now these numbers in maths are usually like 0, 1, 2, 47, but there's also another set of numbers called complex numbers, and this involves the use of the number I. Now a quick definition of I is that I squared equals minus 1. So if you square root both sides, I equals root minus 1. So this is the imaginary number, I. Now you can just treat it like a constant, basically, is how I like to think of it. Think of it as just something that you can multiply any other constant by, but it stays there. So you can multiply it by 2 and get 2i, or by a third and get I over 3. You can also combine both complex and real parts to get a fully complex number with imaginary part and real part. So that will be something like 2i plus 2. Now this is the imaginary part, obviously, and this is the real part. Now usually in exams, for example, if they'd ask to find the imaginary part, you don't put imaginary, let's say if z equal 2i plus 2, you don't put imaginary part of z is 2i. The imaginary part of z is just 2, because it's 2 in the I direction, in this direction right here. And the whole complex number would be 2i in the, 2 in the imaginary direction, and then 2 in the real direction. Now, the number I is, I like to think of it as a circle number. So it does really involve circles later on when you go a little bit more in depth, but there's just a simple thing about the number I. When you multiply by I over and over again on a graph, let's say. So in the y axis you've got imaginary and then real. So let's say if we just do 1 times I, that's obviously just I, which is here. Then if you times I by I again, we get I squared, which is minus 1. So that brings us down to here. And then we times minus 1 by I, which equals minus I. Then we go down to here. So you can sort of see like a circle already forming. Times by I again, we get minus I times I, which equals minus I squared, which then just equals 1. And then we bring it back up to here, which is 1. And then again, obviously, 1 times I, like the beginning, would bring us back up to I. So it sort of rotates us by 90 degrees each time about the origin when we're multiplying by I. So that's one use of the number I, is a little hint, rotation. Now, there's a few questions that we can solve, and it's just trying to find basically the answer to these two questions. Let's say I to the power of 5. So we can separate this into what we know already. We have I squared times I. We know what I squared is right off the top of our head. got minus 1 times minus 1, which is just 1, and then times I. So I to the 5 equals I. Now 1 over I is the same as I to the minus 1. Now, what do we do with this? Because I to the 1 is just I. We can figure out why 1 over I is minus I. First of all, by showing 1 over I is I to the power minus 1. And then also using the fact that I is cyclic. So let's say we've got I to the power 0. Anything to the power 0 is 1. And I to the power 1 is just I. So that's going in this direction, starting from I to the power 0. But we want I to the power minus 1, which is going in the opposite direction of these arrows. So it's minus I in this case. That is obviously useful when you've got a bunch of numbers and you have I times, I don't know, something on the bottom. Usually you want to rationalize this I if it's a whole complex number on the bottom, but if it's just I on the bottom, you can just bring it to the top by changing to minus I. So here we have 3 examples. We have 1 using I pluses and minuses, 1 multiplication and 1 division. So when you're plussing and minusing, again, just treat I as a constant that sticks on there and is visible the whole time. So you have 3I plus 6I, sorry, is just 9I. So you're just keeping it there as if it was like 3C or something like that, plus 6C, just 9C. Then this isn't an I, this is just minus 1. So that's a real part, we just stick that on the end there. Now, using multiplication, this is slightly different because we have to remember that we're multiplying these constants together now as well, these i's. So first let's do 12 from the 3 times 4, and now we want to focus on these 2 i's here. I times I is I squared, and then that equals minus 1. But then we're multiplying it again by I. So in the end, we have minus 12I. Now, this example here, as I explained previously, just has I on the bottom. Now, using the property of 1 over I, we can just flip that to the top as minus I times everything here. And now we just use what we learned from the previous example, minus I times 5I. So first, let's leave the minus out of it and do 5 times I squared. And then we have, let's put another bracket around that, and then plus 1. Sorry, plus I it will be, because we're doing 1 times I. So here the first thing is we equal that to minus 1. I squared is minus 1. So inside of this first bracket we have minus 5, which we times again by minus on the outside, which gives us just 5 minus I. That's our final answer for that one. Now a more challenging question would be something where you don't just have I on the bottom and you have a whole complex number on the bottom. So let's say just I minus 1. So we have an imaginary part, 1I, and a real part, minus 1. So what we do here is we multiply the top and bottom by the complex conjugate. Now, what the complex conjugate is basically the same as rationalizing. So let's say our complex number here is I minus 1. The complex conjugate of this would be just a flipped sign of the complex part, so the imaginary part. So here we have minus I minus 1. Or a better way to put that would be the real part first and the imaginary part second. So we want to times the top and bottom of this fraction by the complex conjugate. Let's do that now. We've got 3i plus 2, all multiplied by minus 1 minus I over I minus 1 minus 1 minus I. Now that, let's do the double bracket expansion on the top. We have 3i times minus 1, which is minus 3i. 3i times minus I, we figured out here, would make it just to a positive real number. So we have plus 3. Then here we have minus 2 from 2 minus 1. 2 times minus 1, sorry. Then 2 times minus I, minus 2i. So you can see here a few terms simplifying. Now on the bottom, I times minus 1 is minus I times minus I is a positive real number, plus 1. Then we have minus 1 times minus 1, which is again plus 1. Then minus I times minus 1, which is positive I. So here on the bottom, the i's cancel out, and we get a real number on the denominator. So simplifying the top, we get minus 5i, 1 minus 5i on the top over 2. So that would be the way to, I call it rationalize, but it's really just multiplying by the complex conjugate. So complex numbers have the usual form of x plus iy, where x is the real part and y is the imaginary part. And as we mentioned previously, the complex conjugate would be flipping the sign in front of the imaginary part to get x minus iy. Now this is useful because if we get z times the complex conjugate of z, it actually cancels down quite nicely to just get x squared plus y squared. We can show that obviously x plus iy all multiplied by x minus iy. So do the x's first. X times x is just x squared. Then do the first x times minus iy is minus iyx, then plus iy times x plus iyx. These cancel. Now we have iy times by minus iy. I remember I times I is minus 1, but then we're timesing it by minus 1 to just get 1. So positive 1. In the end we get x squared plus y squared. Now this result is useful because if you want to find the magnitude of z, so the vector magnitude in 2 dimensions of z is equal to the square root of z times z star. I'm gonna call it z star from now on, which is then obviously equal to square root of I squared plus x squared plus y squared. Now you can think of this using triangles. So let's say you have the point, so from the origin you have the point x plus iy. Now to get to this, you find how many across you've gone. You've gone x in the real axis, and then how many up you've gone. You've gone I you've gone IY in the imaginary axis. Now, if you think of it as a vector instead, so here we have an arrow instead of just a point. We will have the magnitude of x, which is just x, and then we want the magnitude of IY, which is just y. So therefore, the magnitude of the vector z is, using Pythagoras, x squared plus y squared all square rooted. Now the final example I'm going to show you is what is the square root of I? So the first step to this would be just to set z equal to the square root of I, so then we can square z and get rid of the square root off of the I. Z in this case is just the general solution of a complex number, so it's x plus iy. So if we sub in x plus iy into z here, we'll get x plus iy squared equal to I. Expanding this, we get x squared plus 2i xy minus y squared, because I times I is minus 1, and that's all equal to I. Now what we can do is we can minus the I off, and we can find real and imaginary parts of this equation. So x squared minus y squared equals 2i xy minus I, which equals to 0. So this part here is the real part, and actually I should rewrite this bit here. This part here and the 1 before the second I are both the imaginary part. So real, x squared minus y squared is equal to 0, and then imaginary 2xy minus 1 is equal to 0, or just 2xy is equal to 1. Now if we use the real part, we have x squared is equal to y squared. We can obviously cancel that down to x is plus or minus y. Now if x is equal to y, we can sub it in to this one here. We get 2x squared equals 1. So x then equals root 2 over 2, or root 1/2. So that also means that is equal to y. Now, sorry, plus or minus though, because you've got two solutions when you square root here. So finally, subbing the plus x value back into z would give you z is root 2 over 2 plus root 2 over 2i, which is also just equal to root 2 plus root 2i over 2. And then subbing in the negative value for x and y, we get the exact same thing, but just with negatives. So we have a big negative in front of this fraction right here at the end to get negative root 2 plus root 2i all over 2. So that is complex numbers.